So this shows two graphs, one of them showing X versus Y. So it's showing all locations on the wave, but only at one single instant in time. And so that would be a freeze frame in the video, a single paused instant, but all locations. And the other one showing time versus Y. So that's looking at the behavior of one location, specifically the X equals 2 location, but it oscillating up and down as time passes. So two different ways of examining the same phenomenon. And these will both be just different representations of this single equation, Y as a function of position and time. But we can look at these as cross sections, because if you think of Y as a function of X and T, if you have like an X axis and a T axis and a Y axis, that's a three-dimensional graph. But we're effectively looking at a cross section in the X direction and a cross section in the T direction to simplify the look of the graph, rather than trying to draw a three-dimensional graph. And since we've got both of the graphs, we should be able to find every single parameter in the equation. And first of all, what are some parameters, some values we can read just directly off of these graphs? What information in this equation can we find just by examining the graphs?
Amplitude?
Yeah, we can find the amplitude. And how would we do that? If this is oscillating as high as 6 and as low as 4, what would the amplitude have to be? Or how would we find that? Or how do we define amplitude in the first place? That's the distance from where to where. Yeah, one way is to, well, actually the 6 plus -4/2, that would be the average value, right? What is the average of 6 and -4? If we add 6 plus -4 and divide by 2, yeah, we define amplitude as the distance from equilibrium to the crest or equilibrium to the trough. Equilibrium is the halfway point in between. So amplitude would be this difference from equilibrium up to a crest or equilibrium down to a trough. That should be the same distance. So that would be the amplitude. And we don't have equilibrium marked here, but how far is it from crest to trough here? What's that distance? The vertical distance there?
10.
Yeah, from -4 to 6 would be 10. You can find that by subtracting. If it's not already clear, 6 minus -4 would be 10. So the amplitude would have to be
10 divided by 2, so it's 5.
right. We take that difference, 10 divided by 2, to get the amplitude, because the difference from crest to trough should be twice the amplitude. So we can see that the amplitude here has to be 5. And that should really have units attached to it. Let's say Y is measured in meters, amplitude would then be 5 meters. And by the way, Y doesn't have to be measured in the same units as X. Y and X don't really directly interact here. The only time you need to have them in the same units is if you're finding the slope. So Y could be in meters or centimeters. It might not even be measuring distances. If you're talking about a sound wave, Y would be differences in pressure. So amplitude would be measured in pascals. But let's say it's also in meters just for simplicity. So that's amplitude, 5 meters. Whereas if we wanted to find this equilibrium value, this halfway point, how would we find the point halfway between 6 and -4? Yeah, in that case, we could find the average. So one way to do that would be to add the two numbers, 6 plus -4, and divide by 2. So what would that be? What's halfway between those?
So it's 1.
Right. And we usually call that Y equilibrium or Y sub 0. So that's just the equilibrium point that everything's oscillating around. We go one amplitude above equilibrium and one amplitude below equilibrium. And I haven't actually written that in the equation, but where would that show up in the equation? How would you modify the equation so it's oscillating around 1 instead of oscillating around the axis?
Isn't, if it's on the left, it should be y minus y0, or if you put it on the right, then it's plus
Yeah,
y0. Oh, why not? Sorry.
yeah. Yeah, I think that's probably a good way to write it, because that way, if you just add a constant to a function, just in terms of the mathematics, what happens to a graph if you just add a constant to the function?
It doesn't change.
It doesn't change the shape, but what does change? Like if you graph y equals x squared and then graph y equals x squared plus 5, what difference would that make to the graph? Yeah, it's just going to shift it up. Whereas if you wanted to shift left and right, what would you do? Like for instance, sorry, go ahead.
I was going to say, if you shift it left and right, you would, so if we're using the y equals x squared example, would be y equals x squared minus 1 or something?
X squared minus 1, how would the minus 1 shift it? That's not going to shift it to left or right. That would shift it in which direction?
Oh, it would shift it down. So
Yeah.
to change it, it would be y equals parentheses x minus 1 parentheses squared, right?
Yeah, exactly.
Okay.
If you make a modification by adding or subtracting a constant outside the function, that's most directly influencing the resulting y value. So adding or subtracting outside the function shifts the function vertically. But if you make an addition or subtraction inside the function, in this case, before you square it, that shifts left and right. And the same thing applies to a sine function. The plus y naught outside the sine function is a vertical shift in the wave. The plus phi inside the sine function would be a horizontal shift, called the phase shift. So that's really one way to think of the plus little phi, the plus the phase shift here. That represents a horizontal shift. But the thing is, since the wave is in motion anyway, it's probably best to think of phi not as moving the wave, because it's already moving, but really phi is more about these starting conditions. Because in terms of the starting conditions, let's say we're talking about time 0, the beginning of the experiment, and position 0, the location we're calling the origin. If there's no phase shift, like let's say we had a wave that doesn't have a phase shift at all. If we leave that out, if you plug in 0 for t and 0 for x, what do you get for the resulting y value? What is sine of 0? Yeah, that'll just be 0. So if we didn't have a phase shift term, if there was no plus phi inside the sine function, every wave would be passing through equilibrium at time 0, or passing through the origin at time 0. That's not true. We want to be able to have a wave that's passing through any height, any point in the wave at time 0. So the reason we need the phase shift, the plus some constant here, is to account for the initial conditions, to account for the fact that the wave doesn't have to be passing through the origin at time 0. It could be passing through any point at time 0. So that's really what the phase shift represents. It represents it allows for a variability in the initial conditions. And as such, it's not really a value you can read directly off the graph. Like all the other values, we can just look at the graph and make some measurements and fill it in. Phase shift is typically the last thing you find, and you find it by solving for it algebraically after finding everything else. So let's go ahead and find everything else. We've got amplitude, we've got y naught. Can we find period and wavelength from these graphs? How would we do that?
So period is defined as from one, how long does it take from one point to go to exactly the next one point?
Yeah, so which graph should we examine to find period?
The bottom one.
Right, because period is an amount of time. It's the amount of time it takes, for one full cycle, from a certain point on one cycle to the same point on the next cycle. So we'll want to find maybe a crest on 2 adjacent cycles, like same crest on one cycle, crest on the next cycle, or trough and trough. And do we have any of those that would be easy to measure here, anywhere we know the values?
I think it's the point that is intersect with the x vertical the x axis at 3. And
Yeah,
that
well, at 3, it's not quite on the axis, it's at equilibrium, but that's actually good because equilibrium is a very reliable point to look at. So we've got a point where the wave passes through equilibrium. And when is the next identical time?
the one is at 5.
Yeah, or I guess that's 4.5 because each of these markings is half of a second.
Oh, okay.
And you've got to be careful about that. We wouldn't want to look at this one because even though those are both equilibrium, these are not really the same point on 2 adjacent cycles. Equilibrium on the way up and equilibrium on the way down are not the same. If you choose equilibrium on the way up, you want to look at another point on the next cycle that's also equilibrium on the way up. If you do choose 2 points like this, equilibrium on the way up and equilibrium on the way down, that's not actually the period, but it is what fraction of a period?
T 1/2 of the period.
Yeah, and that is sometimes useful. If you don't necessarily have a full period that's easy to measure, if you can at least measure from equilibrium on the way up to equilibrium on the way down, or vice versa, or like from a crest to a trough, that's a reliable exactly 1/2 of a cycle. So if you can measure the amount of time from crest to the next trough, or from trough to the next crest, or from equilibrium on the way up to equilibrium on the way down, that's exactly half of the period, and then you could just double that. In this case, though, it looks like we can measure the period directly from equilibrium on the way up to the next equilibrium on the way up. How much time is that? How much delta t?
Right. 1.5 second.
Right. So that'll be the period, capital T, 1.5 seconds. So we'll list that as well. Period is 1.5 seconds or 3/2 seconds. Sometimes it's easier to work with it in terms of fractions. What about wavelength? Where should we look to find that?
You would want to look at the y versus x graph.
Yeah, on the y versus x graph. And this is one of those cases where we can't really directly see the wavelength here, because this graph is a fairly small span of distance, only from 0 to 10. It looks like the wavelength is even longer than that. Like one full cycle from crest to the next crest. Looks like the x equals 0 is not quite at a crest. The crest is a little before that. And then the next crest looks like a little after the end of the graph. So one full cycle from one full wavelength from crest to crest is larger than the distance we have available to see. So instead, we should look at some useful fractions of a cycle. For instance, if we go from, let's say, equilibrium on the way down to equilibrium on the way up. How far is that?
So is it half of the wavelength?
Yeah, that's exactly half of a cycle. And we can kind of see that on tracing out the curve also. This portion of the curve, a full wavelength would be like this. Here we only have half of a wavelength. So this much is half of a wavelength. So with half of a wavelength, we can at least write out an algebraic expression. We can say wavelength over 2, half the wavelength is from 2 to 8, that'd be 6 meters. So then what would the wavelength be?
12.
Yeah. Wavelength equals 12 meters. And you could use other fractions as well. For instance, if you notice that you've got equilibrium at 2 and the next trough is at 5, that's 3 meters. And how much of a wavelength is it from equilibrium to the next trough? Right, 1/4 of a wavelength. So you could say wavelength over 4 equals 3 meters. Multiplied by 4, you get 12 meters again. So either way, we get wavelength is 12 meters. And I think that's just about everything. If we fill in everything we've got so far, let's see what we've got. We fill in amplitude is 5 meters. Period is 1.5 seconds. Wavelength is 12 meters. And we also know the Y naught is 1 meter. So it looks like we've got all the parameters except for phase shift. Although to find that, we're also going to need to decide whether to use plus or minus here. And what determines that? What determines whether we use plus or minus?
So isn't if the wave is moving to the right, then it's a minus, or if it's moving to the left, it's a plus.
Right. So we're going to need to figure out which direction this wave is moving. Any thoughts on how we could do that? If we've got a position graph and a time graph, how could we combine those to get information about which direction it's moving?
So first we identify the common points between the two graphs, and then we figure out if it makes sense if that point is like going down or like going up, if the wave is like moving left or right.
Yeah. For example, for the first graph, it tells us that this whole graph, we're looking at lots of x values, but only one time value, 3 seconds. Where else can we find information about time 3 seconds?
The bottom graph?
Yeah, on the t versus y graph, we have a point that is time 3 seconds. Likewise, this graph, the t versus y graph, is all times, but only one position, x equals 2. But we can find x equals 2 on the top graph, the x versus y graph. So these 2 points I've just marked are really the same point. They look different because they're being shown from different perspectives, but that's the intersection of those 2 cross sections. We got a cross section in the x direction, a cross section in the t direction. This point represents the intersection of those cross sections. Or in terms of coordinates, if we list out the coordinates here, this is x equals 2 meters because it's that point on the graph. Time is 3 seconds because this whole graph is 3 seconds. And it looks like the y value is 1 because it's passing through equilibrium. Whereas if we take a look at this point is time 3 seconds as shown by the graph. X equals 2 meters because the whole graph is at 2 meters. And it looks like y is passing through equilibrium, so that's 1 meter. So even though these points look different, their coordinates are exactly the same. X equals 2, t equals 3, y equals 1. So those are just 2 different depictions of the same data, the same information. And that's what we mean by a point in common. Any questions on that point in common so far? So both graphs are saying that when time is 3 seconds, then the 2 meter location is at a height of 1 meter. And can we figure out what's happening next? Like, is that 1 meter on the way up or 1 meter on the way down?
So it's 1 meter on the way down.
And how can we tell?
So we're looking at the graph above. So it's that 1 meter on the way down.
Which graph?
The graph above. The y versus x graph.
For the y versus x graph, though, what does this one have to do with time? Is this one describing the behavior, or is this one frozen at an instant in time?
Frozen at instant of time.
Right. So this one doesn't really tell us what's happening next. This one tells us what the graph looks like a little further to the left or a little further to the right at that one instant in time. But remember, this is not an animated graph. This is just showing one frozen moment in time. If we want to figure out what happens next, we should be looking at which graph?
Then the bottom one.
Right, because that's time versus y. This one is actually showing the behavior as time passes of one location. the one location we're concerned with here. So we don't really care about the other locations. We're looking at what's happening a little bit later in time. So if you start at this location we've marked as the point in common, a little further forward in time, has that point moved up or down? Yeah, the positive slope suggests that this point is on its way up. As time passes, the y value is increasing. So we know that at time 3 seconds, the 2 meter location is at 1 meter in height and on its way up. So we can take that information to here as well. We know this point is at 1 meter and on its way up as time passes. So now let's see what this would actually look like. If we imagine turning this into an animated graph. Let me sketch this out. We have the graph of this shape. And remember, the x equals 2 meters location isn't moving left and right. It's just oscillating up and down. But we can take this wave and imagine that the wave is sliding to the left, or we can imagine that the wave is sliding to the right, or other way around, sliding to the left or sliding to the right. Which direction of wave motion would involve this 2 meter mark on its way up? Yeah. If the wave is moving to the right, that would force this one single point to be sliding up or oscillating upwards so that it's still on the graph. So we know that this wave must be on its way to the right, because if it was moving to the left instead, moving to the left would mean that this point would have to move down to match. And that doesn't make sense. We want this point to move up instead. So that tells us this wave must be moving to the right. Another way to look at it that might make more sense, depending on how you think about it, is that if we want this point to move up, should the nearest crest or the nearest trough be moving towards it?
The near crest?
Yeah. And the nearest crest is this location here, or somewhere around this location. So if we want the nearest crest to move towards it, that crest has to be moving to the right, which means the whole wave is moving to the right. So we should expect this wave to be moving to the right based on the behavior of that point in common. Any questions on that motion so far? So to recap, we found a point in common. We used the time graph to figure out at that instant in time, is the point on its way up or on its way down based on the slope. And then visualize moving to the right versus moving to the left on the x graph, and which one of those actually involves that point being pushed in the correct direction. In this case, upwards, which means the graph has to move to the right. Or alternatively, think of it in terms of, should you expect the nearest crest or the nearest trough to be moving towards that point? So we know this is moving to the right. Or alternatively, we could say in the plus x direction. And that tells us, should we use plus or minus in the equation itself? Okay, so based on the equation we've got so far, with everything known, even the direction of travel and phi, the phase shift, being the only unknown left, this is actually a very good place to be in. As soon as we've got an equation narrowed down to only one unknown parameter left, we can solve for that. Except for one thing, what other variables do we still have in this equation other than phi? We've got phi and also what other variables?
Y?
Yeah, y and also, yeah, x, t, and y. But we can get values for all of those because we've got all these graphs. The graph is a whole set of data, a whole set of values for x and y and t. So we could choose any point on this graph because the graph is just a set of points that make the equation true. choose any location on either of these graphs and fill it in for x, t, and y. And then phi will be the only unknown left. One thing to be careful about, there can sometimes be some ambiguity. Like for instance, if we were to choose, let's say this location, let's say at a height of y equals 3 maybe. The problem is there's another location that's also height equals 3 on the same cycle, on the same period of the graph. So it's generally not a good idea to choose a point like that because there's ambiguity. The equation doesn't know which of those points you're talking about if you just fill in 3 for y or whatever. But what's a location or type of location that only shows up once in each cycle?
Could you pick a minimum or a maximum?
Yeah, a minimum or a maximum, a trough or a crest. So what you want to do in cases like this is choose a crest or a trough, a maximum or a minimum, at a location or at a point on the graph whose coordinates you can be very certain about. So do you see any crest or trough here that has coordinates that you can easily determine? Like ideally a whole number or a nice convenient fraction that we can directly read off of the graph.
Can you please repeat the question?
Do you see any crest or trough on either one of these graphs that has coordinates that are easy to read in terms of nice, neat whole numbers or convenient fractions? Yeah, 5, -4, specifically on the x graph. If we consider that location, the location at x equals 5, y equals -4, that's definitely a trough, a minimum. So let's label that. We've got a trough or a minimum at x equals x equals 5. And yeah, you can pick a crest or trough from either one of the graphs, as long as you can read the coordinates off of it clearly enough. Like here, this trough is definitely at x equals 5 meters, I should say. And also what t value, because we got to have a value for x and a value for t. This is at x equals 5, but what's the t value for this point on the graph? Yeah, this whole graph is time equals 3 seconds. So x equals 5 meters, because that's the point on the graph, t equals 3 seconds for this entire graph. Or if we had used a point on the other graph, we would use the t value for that point on the graph. We might have to estimate, unless we had more detail on the axis. And then x would be 2, because this entire graph is at 2 meters. But since we're using this point, it's x equals 5 as shown on the axis, t equals 3 because that's the entire graph. And if we need it, y is -4 meters. So we can now fill in that x value, that t value, that y value. So the whole equation exactly as is. But replacing y with -4 meters, replacing time with 3 seconds, replacing x with 5 meters. And that is now an equation that could be solved algebraically for phi. And what steps would you take there? What would be the first few steps for algebraically solving for phi here?
So -1, yeah, -1 for both.
Yeah, subtract 1 from both sides. -4 becomes -5. And then
Divided by 5, and then
divided by 5. And note that we now just have sine equals -1. We could actually start there. We could say, since this is a trough, sine has to be the sine function, ignoring everything else, the -5, the +1, ignoring everything else, the lowest sine can get is -1. So we could just skip that and say, assume that sine of whatever equals -1. And then how would you undo the sine function?
Arc sine?
Right, take the arc sine or inverse sine of both sides. In other words, we're trying to find an angle whose sine is -1. And what angle is that? What input could you use to make the output -1? Yeah, it should be 3 pi over 2. And there's a couple of ways we could get there. We could say the inverse sine of -1 is 3 pi over 2. But yeah, we could also say, well, we know we want the sine to be the lowest possible. One way to get sine to be the lowest possible is to use 3 pi over 2 as the input. So we could actually just skip directly to that. Instead of going through all the algebra, we could take a shortcut and look at just what's inside the sine function. What's inside the sine function? Just this piece. This is called the total phase. Total phase is just a fancy way of saying the entire input inside the sine function. And that total phase, in order to get a trough, the total phase has to be 3 pi over 2. Because sine of 3 pi over 2 is -1, which is the lowest it can get. And it doesn't have to be exactly 3 pi over 2. You could also go, how much further could you go and be at the next trough? How far in terms of angle do you have to go to get through one full cycle?
2 pi.
Yeah, one full cycle worth of angle is 2 pi. So if you're looking at the unit circle, if you're at the lowest point on the unit circle, that's 3 pi over 2. One more full cycle is 3 pi over 2 plus 2 pi, or 3 pi over 2 plus 4 pi, plus 6 pi, plus 8 pi. Every extra plus 2 pi loops you back around to the same point. So what we can do, since we're at a trough, we could skip everything else and just say the total phase, the stuff inside the sine function, equals 3 pi over 2. Or 3 pi over 2 plus an extra 2 pi, or plus an extra 4 pi, or minus 2 pi, minus 4 pi, minus 6 pi. Any extra plus or minus 2 pi doesn't actually change the result. But let's just say 3 pi over 2 for convenience. Or alternatively, if you were at a crest, what would you use for the total phase? Yeah, at a crest, the total phase is pi over 2, because sine of pi over 2 is 1, which is the highest it can be. So if you're at a trough, set the total phase equal to 3 pi over 2, plus or minus any whole number multiple of 2 pi. If you're at a crest, set the total phase equal to pi over 2, plus or minus any whole number multiple of 2 pi. And then you can solve for phi, the phase shift. And we will probably want to simplify things first, like 3 seconds over 1.5 seconds is just 2. Seconds cancel out. So 2 pi times 2 would be 4 pi, minus meters and meters cancel out. 2 times 5 would be 10 over 12, so that'll just be 5/6. Plus the unknown phase shift equals 3 pi over 2. And then we'll just need to solve for phi. And to solve for phi, what would we do? Like, how would we cancel out the 4 pi? What's the opposite of this 4 pi here? Or how would we algebraically get rid of a plus 4 pi?
Subtract it from both sides.
Yeah, subtract 4 pi from both sides. Although since that's 4 pi, there's a nice shortcut we can use there. 4 pi is how many cycles? If you take some angle and go exactly 2 cycles, exactly 4 pi, have you changed the angle?
No.
So that means we can actually just ignore this 4 pi entirely. Since it's exactly a whole number of cycles, it can be ignored. You could certainly include it, but any whole number of cycles being added or subtracted can be ignored since it doesn't actually change the result. So I would just ignore that 4 pi since it's a whole number of cycles, and then we could just add 5 pi over 6. So let's add 5 pi over 6. Phi equals 3 pi over 2 plus 5 pi over 6. And what's our common denominator there?
6.
Yeah, so we'll just convert 3 pi over 2 into sixths, multiply numerator and denominator by 3. 3 over 2 becomes 9 over 6. So we get 9 plus 5 would be 14 pi over 6. Or reducing that, we get 7 pi over 3. So we could use phi equals 7 pi over 3. But it would be a little more convenient to make that smaller because 7 pi over 3, that's more than 2 pi. That's more than one full unit circle. And what could we always add or subtract to an angle that doesn't really change its value?
2 pi.
Right. So if your phase shift is a number that's more than 2 pi, then I would subtract 2 pi until it gets down to as small as you can get while still being positive. Or if you get a phase shift that's negative, I would add 2 pi until it becomes just barely positive. Like here, let's go ahead and subtract 2 pi from this. That is, we're subtracting 6 pi over 3, so we get 1 pi over 3. So that's what I would use as the phase shift. 7 pi over 3 will work, or if we had included the 4 pi, the result we get would work. But it's easiest to use, and I guess most consistent, if everybody's using the same phi value for the same wave. So we standardize this by expecting the phi value to be somewhere between 0 and 2 pi. So I would use pi over 3 here. We can now fill that into our original equation, replace phi with pi over 3. And this is now our equation for the whole wave. And notice that this equation applies to both the x graph and the t graph. We could use this equation to generate more x or t graphs at different times or different positions. We could use this equation to predict what the height's going to be at any time at any position we care to look at. This equation describes everything there is to know about the wave. Any other questions on that?
Hi, Casey. So I just want to confirm on the amplitude is from the equilibrium to the crest or to the trough.
Yeah,
right?
and that should be the same distance because the equilibrium is exactly halfway between crest and trough in terms of vertical distance.
So to find the amplitude, we figure out the distance between the trough and the crest, and then we divide it by 2.
Yeah, that would be one way to do it. Or you could find equilibrium first by taking the average and then look at how far is it from equilibrium up to the crest or from equilibrium down to the trough.
Okay, and
Once you know equilibrium is 1, you could just say 6 is 5 above that. So the amplitude is 5.
so the equilibrium is the y naught.
Yeah, and that'll be the average of the highest point and lowest point, exactly halfway between.
Okay, thank you.
You're welcome. Any other questions? All right, then I will see you next time.